So, in last 4 classes we have demonstrated how to measure the focal length of concave mirror, convex mirror, concave lens, convex lens, right. So, we have used the basically parallax method, means using the image needle, we are trying to find out the position of the image by parallax method basically. So, tip of the image and tip of the image needle. So, they will coincide and they will not be separated when we are moving our eye towards left and right. So, today I will demonstrate another method for measuring the focal length of a convex lens. So, that is it is called displacement method. So, what is that displacement method? So, let me explaining. So, basically determination of the focal length of a convex lens by displacement method. Okay. So, this formula, working formula for this method or this lens formula is basically 1 by f equal to 1 by v minus 1 by u, right. Now, displacement method is basically if the distance between the object and the screen is greater than 4 times of focal length of a convex lens, sharp image is formed for 2 position of the lenses. If x is the displacement of 2 position of lenses and d is the distance between object and the screen, okay, then this focal length of the convex lens is equal to d square minus x square divided by 4d. So, this is the working formula for this method, displacement method. Okay. So, basically we have to keep object and screen at a fixed distance, and that should be greater than 4 times of focal length of the lens. Now, if we move this lens between this object and screen, so for a one position we will get sharp image of the object on the screen. So, we have to note down that position, and then if we move again you will get another position. For that position of the lens you will get again the sharp image on the screen. Okay. So, this is displacement of this lens for getting the sharp image twice on the screen. So, this x we have to find out, and position of the screen and the object are fixed. So, that distance we have to note down. So, that is d. So, now using this formula we can find out the focal length. So, keeping the screen at different distance, say 5 centimeters more distance, or yes 5 centimeter, 10 centimeter from this position. So, we can take 3-4 sets of the data and we can find out the f, and average f we can get, right. So, how this formula has come, I think this is the 12 class task, you know. So, this is a homework, but I can show you how it has come, but I do not think I need to explain more, because this is the image, this is the object, and this is the image screen position. Okay. So, this is a position of the lens. So, distance of this lens, or the distance of the object from this lens is u, and this distance of the screen from this lens is, so that is the image distance v. Okay. For this position of the lens, we are getting the image on the screen. Okay. Now, if you find out the second position of the lens, from where you are getting the again image at the same place. So, that means the object distance will be this, and image distance will be this, right. So, basically whatever the case, d, this total distance d equal to u plus v. So, v equal to d minus u. So, in this formula 1 by v minus 1 by u equal to 1 by f. So, you can replace v by d minus u. Okay. So, then you simplify it, then you are getting quadratic equation of u, that means you will get two solution for u. So, so u1 and u2, So, basically this is the one position of the lens. So, this distance is u1, and second position of the lens, that is the u2. So, basically u2 minus u1 is basically x, u2 minus u1 is basically x. So, x equal to u2 minus u1 equal to, from here is subtract it, you will get this. So, from this relation, f equal to d square minus x square by 4d. Okay. So, this is the working formula for our experiment. So, for our experiment, we will use the table, this table. Okay. So, actually I make the table, so it can be single lens or it can be combination of two lens. Okay. So, but here I am discussing only for single lens. One can do the experiment same way using the combination of two lens, either they are in contact or they are separated by distance d. Okay. So, number of observation, now position in centimeter of object and screen, right. So, this from this position you can find out the distance between the object and the screen, that is capital D equal to OI. Okay. So, now we have to put the lens and find out the position, in centimeters in case of say single lens. So, for first position we have to note down, for second position we have to note down. Okay. So, observation generally for each case you can take 3 observation, and average of O1 for first position, average of O2 for second position, and then displacement you can find out x equal to O2 minus O1. Okay. O2 minus O1. Okay. So, for combination of lens also one can do, but I think same way one has to do. I will skip it. So, you can find out the focal length, using the formula d square minus x square by 4d, either for single lens or for the combination of the lens. Okay. So, both you can do, if you can do the single lens and then combination of the another, if you combine another lens with this single lens whatever we have used. So, from this table you will get the focal length of the single lens, and from this table you will get the focal length of the combination, lens. Okay. So, if that is capital F, so you can find out the focal length of the second focal length F2 of the second lens. Okay. So, but that part I will skip as I told. So, that is I am leaving on you. So, it is your homework, you can find out, but here I will demonstrate how to find out the focal length of a convex lens, single lens, okay, by displacement method. Okay. So, let me demonstrate the experiment. So, here actually I need screen. Earlier I was using the image needle and using the parallax method to find out the position of the image, but in displacement method uh, we cannot use the image needle, okay, because in this method we have to find out the two position of the lens. For that position of the lens, how I will find out the position of the lens? Seeing the image, sharpness of the image, I can find out the two position of the lens. So, that is why I have to see the image directly, then only I can use this method, displacement method. So, here this is a screen and this is a needle. On needle actually I have put a wax, I have put a small wax. Okay. So, I will lighten it, and then this is basically our source object, and then we will see the image of the candle on the screen, and we will try to get the sharp image of the needle. So, it will be basically inverted. So, for another things, for these two position, for first position near to the lens, near to the object. So, we will get larger, we will get magnified image, and for the far distance we will get very small diminished image. Okay. So, that from theoretically one can check it, find it. Okay. So, let me lighten it. So, this is my object, okay, and this is my screen, right. Now, let me see find out the position. You can see this, I can see the image here, but it is the defocused. So, I have to find out the focused image on the screen. Yes, again going to be defocused. Now, I exactly, yes, you can see the inverted image of this candle. Okay. So, I have to note down this position. So, in my table I will note down the position. So, observation 1, okay, observation 1. So, this position of the object is 0, I kept it 0, okay, and then screen position I have kept it at 50, screen position I have kept it at 50 centimeters, okay, the reading. Okay. Now, this lens position I can see 12.2, I can see lens position. So, this is distance is with D, capital D is 50, and then first position of lens I can see this is 12.2. Okay. Now, I will find out the second position. Now, you see is defocused, I am going, and then now I am, it's focused one I am getting, but smaller one. So, you can see smaller one again going to be defocused. So, yeah, I think this position I can take, this position I can take, okay. This position I can take. So, that is why basically it is not the unique position. So, actually one should take three reading for this, also for this position one take. What is the position here? It is the 42.7. It is the 42.7, 42.7, okay. I can see 42.7. So, you can just move and take two more observation, and I am not going to take, but you should do that. Then you take the average one. This is 12.5, 12.2, and this is 42.7, okay. So, now I am getting displacement x, O2 minus O1. So, I can see this is 5, and then it's I can see it is 0, 0, and then 3, okay. 30.5 is the 30.5, okay. So, approximately say it is 30, for calculation it will be here. Now, d square minus x square divided by 4d, okay. So, if I calculate, what I am getting? The capital D is 50 and x is 30. So, if I calculate using that formula, f equal to d square minus x square divided by 4d, okay. So, measurement what I have done, this is the 50 square minus 30 square divided by 4 into 50, okay. So, this is basically a square minus b square. So, a plus b is 80 into a minus b is 20 divided by 4 into 50. Here I can, so let us take out 0, then this is 4 and this 4, okay. So, it is the 8, if I am getting 8 centimeters, okay. So, approximately I have done, and I am getting it is 8 centimeter, okay. So, you should take 2 more, 3 more observation and find out the actually it's not 8, it should be around 10, it should be around 10. So, it is 10, it was 30.5 basically. I think I have not done mistake in calculation, 30.5, yes. So, if you take 30.5, it's square. So, it's higher, so it will be smaller, I do not know. Then it may be okay. So, if it is higher, then this difference will be lower. So, this may go down, okay. Anyway, so just approximately I just find out that is 8 centimeter, but this lens is approximately 10 centimeter, but it may not be the it is 10 centimeter, it can be 8. So, this is the way one has to actually find out the, you see. So, again if I do experiment, yes. So, I will take this position Now it is again 12.3, earlier it was 12.2, now it is coming 12.3. Okay. So 12.4, so it is coming around that point. Okay. Okay, around 12 point. So second time I will see. This it is 43.5 it is coming. Okay, so one mistake I have done here, I can see it is not 50, it is 56. That is the mistake I have done. So, that is why the result was come, it is not 50, I can see it is 56. So, it is basically screen distance is 56. So, the screen distance is 56. Okay. So, I think that is the mistake I did. So, that is the result was the way, and this value twice I checked, this more or less this. So, this is 30.5. So, approximately 30 you can take, or 30.5 also, approximately 30. So, in calculation actually we have to make it 56. Okay. This we have to make 56. So, if 56, let us take 30. So, it will be 86. So, it will be basically 86 into 6 to 26 divide by 4 into 56. So, it is up to 13. No, it will not go. I think it's the 13, and then it is 2, then this is 43. Okay. So, it's a 43 into 13 divided by 56. Now, let me use the calculator. Let me use the calculator to find out. So, this is the 13, 43 into 13, 43 into 13 into 13, then divide by 56, divide by 56 equal to, divide by 56. So, it is again equal to this, I do not know, this calculator. So, this 43 into 13 equal to 559 divide by 56 divide by 56 then equal to, but unfortunately here it is 559 by 56, then answer I want 559, calculator, 559 divide by 56. Okay, answer I think I will use another something wrong. 559 divide by 56 equal to, yes, it is coming 9.4745. Okay. So, it is a 9.5 centimeters, approximately 9.5 centimeter, right. So that is why it was earlier it was coming 8. So, because I did mistake, so it should not be. So, this focal length of this one as per company is telling, that is 10 centimeters. So, our measurement is coming 9.5. So, now if you take 30.5 or if you take more observation, so it may go close to 10, okay, or whatever you will get, that is the your measurement value. Okay. So, this is a very useful method, simple method, displacement method, but you need screen, and I think yes, for that you need the real image which you can see on the screen. So, that is the condition to use this displacement method. So, now with this one, if I put another lens, if I put the another lens, okay, and these two lens, either they can be in contact or they may have some separation. Okay. So, then that focal length will be combination of this focal length f equal to 1 by f1 plus 1 by f2 minus d by f1 f2. Okay. So, what is the d? D is the separation between these two lengths. So, changing the separation of these two lengths, you can get the variable focal length of this combination. So, that is the advantage of this one. So, this experiment also one can demonstrate using this method. Okay. So, I am not going to repeat that one. Also, you can measure the focal length. So, you can find out the equivalent focal length of these two, and from that one you have measured already. For second one, you can find out that focal length of the second one. Okay. If you get this one from this method, basically you will find out this one. Okay. For one, if you know, so other one also you can find out. So, this other one, it can be concave lens, this can be also concave lens. Okay. For concave lens, directly using this one we cannot find, but only condition that concave lens, that focal length, it should be greater than the focal length of the convex lens. So, ultimately then if it is focal length of convex lens is less than the focal length of the concave lens. So, this resultant one, it will be basically converging lens, concave lens. So, it will form the real image, okay, and you can see on the screen. Okay. So, this is another method we use for measuring the focal length of convex lens or combination of the lens. Combination of the lens also, as to find out the focal length of the concave lens. So, we have to take help of the convex lens. Okay. Because concave lens, it form the virtual image that we cannot see. Okay. We cannot put on the object image needle, right. So, that is why we need to take this help of the convex lens, but I showed you another method. So, from here, using this combination method, combination of the lens and using the displacement method, also you can find out the focal length of the convex lens, or you can find out the focal length of the combination. You can find out the suitable distance, for which distance you should keep these two lengths, so that you can get your desired focal length for some purpose. Okay. So, this is the displacement method we use in lab, apart from that parallax method. So, I will stop here. Thank you for your attention.